Hello everyone, I'm Mehmet Kerim Yücel, and I'm pleased to present LRA&LDRA, Rethinking Residual Predictions for Efficient Shadow Detection and Removal, which is a joint work between Samsung Research UK and CERT-ITI Greece. Shadows have a large impact on vision. They provide cues for seeing geometry and also negatively impact the performance of other vision tasks. Detecting and removing the shadows are therefore of great interest. Shadow detection and removal have unique challenges, such as unconstrained scenes, hardship of data collection, poor in-the-wild performance, and the use of large models in the literature. We have a simple goal, a device-friendly model that performs well in an efficient manner. We identify two major goals, improving our accuracy and addressing the dataset limitations in the literature. First, we focus on the accuracy. Many existing methods simply reconstruct the whole image during removal, which includes the non-shadow area that should not change. This wastes network capacity and leads to high non-shadow area error. Residual prediction methods have a residual connection from the input to the output, therefore they only predict the difference. However, this leads to boundary errors and poor refinement performance in practice. We rethink residuals in a simple manner. Taking normal residual connections as a special case, we propose LRA and LDRA modules that operate over the input and the output of the network. This is a generic framework that aims to better guide the removal to focus on shadow areas and also perform blending and color correction in a computationally cheap way. We need LRA and LDRA to have a strong spatial component and a strong channel-wise transformation ability while being as lightweight as possible. To this end, we use coordinate attention blocks for both modules. Note that any function can be used to implement our modules, and we provide ablations on this in our paper. Now, we focus on the data limitations in the literature. Existing real-life datasets are small and controlled. Synthetic ones are larger, but lack mask and shadow-free image diversity. The bottleneck in scaling synthetic datasets is simple: how to find unique shadow-free images. We propose a simple pipeline to alleviate this. We simply take any dataset, extract shadow-free patches by using a shadow detector, and cast shadows on them using a diverse set of masks. We end up with pizza that is significantly larger and more diverse than any dataset in the literature. Refer to our paper and supplementary material for detailed analyses. And finally, the results. We use a stacked CNN pipeline for joint detection and removal. LRA and LDRA modules are plugged into the removal network. Both modules successfully work across different architectures, and they even improve existing methods. We then take pizza as a pre-training dataset. Pizza improves the performance of LRA and LDRA, as well as other methods. It comfortably beats other large synthetic datasets on pre-training performance too. We now compare ourselves against the state-of-the-art in shadow removal. We use a lightweight backbone for our stacked CNN setup with LRA and LDRA. We achieve best results with LRA and LDRA, which become significantly better with pizza pre-training. We now focus on shadow detection. Although we do not use any post-processing steps on the predicted masks, we achieve on-par results with the state-of-the-art. With pizza pre-training, we comfortably outperform all other methods. We achieve state-of-the-art results with a fraction of the complexity. LRA and LDRA at negligible overhead. Our final setup consumes up to 150 times less memory than others. In short, LRA and LDRA are faster, better, and can be plugged into any architecture or method. Pizza is the largest and most diverse detection and removal dataset in the literature. It improves not just our method, but other methods as well. Thank you for listening to our presentation, and feel free to ask questions.